consequences for our everyday lives, and they are key to understanding the philosophical implications of quantum mechanics. Imaginary numbers are used in Schrödinger's equation, and they are used in fields such as stability analysis, AC current analysis, and many others. Yet these are numbers that are impossible to see or touch. The only numbers that we can physically see and touch are positive real numbers, which are represented by this number line. But there also exists another very useful set of numbers called negative real numbers, which are represented by this other number line. In addition to positive and negative numbers, there exists yet another set of mysterious numbers which are just as real, even though we have chosen not to refer to them as real. Instead, we have decided to refer to these numbers as imaginary, and these are represented by these two new number lines. A number can appear anywhere along any of these four number lines. A number can also appear anywhere in the plane formed by these number lines, in which case the number is the sum of a real number and an imaginary number. The set of all the numbers that can appear in this plane are what we refer to as complex numbers. We can represent each complex number as an arrow, as shown. When two complex numbers are added together, their arrows add together like vectors to produce the result. This means that their real portions will add together, and their imaginary portions will add together. A complex number can be represented by its real component and its imaginary component. Or, the complex number can instead be represented by the length of its arrow, and the angle that this arrow makes with the positive real axis in the counterclockwise direction. Suppose we have two complex numbers, represented by these two arrows, and we multiply them together. Their product will be represented by a new arrow. The length of the new arrow is the product of the length of the two original arrows. And the angle of this new arrow is the sum of the angles of the two original arrows. The length of the new arrow is the product of the length of the two original arrows. And the angle of this new arrow is the sum of the angles of the two original arrows. Suppose that we have a number that is represented by an arrow with a length of 1 and an angle of 90 degrees. We will refer to this number as I. If we multiply I by itself, the product will be represented by an arrow. This arrow will have a length of 1 multiplied by 1. And it will have an angle of 90 degrees plus 90 degrees. Therefore, the new arrow will have a length of 1 and an angle of 180 degrees. This number is -1. Therefore, I multiplied by I is exactly equal to -1. We can represent this by saying that I squared is equal to -1. Or we can represent this by saying that the square root of -1 is equal to I. If we have a function with only real numbers as inputs and outputs, then we can represent it like this, with one axis for the input and one axis for the output. If we have a function with complex numbers as inputs, then we need two axes just to represent the input. We need one axis to represent the real part of the input, and the other axis to represent the imaginary part of the input. The output of the function is also a complex number which would need two additional axes to be represented. The output of the function is a complex number that can be thought of as an arrow with a length and an angle, as was shown before. Let us call the length of the arrow the magnitude of the output. And let us call the angle of the arrow the phase of the output. But since we already have two axes for the input, and we are limited to only a total of 3 spatial dimensions, let us represent the output with just a single axis. This new axis will only signify the magnitude of the output using a logarithmic scale. The phase of the output will be signified by the color. This is the graph for the function where the output is exactly equal to the input. The magnitude of this function at the center of the graph is 0. When the magnitude of this function is 0, it is represented on a logarithmic scale by the center of a bottomless funnel, due to the fact that 0 on a logarithmic scale is represented by a number that approaches -infinity on the axis. Now let us consider this other function. Here, the magnitude of the function at the center of the graph approaches positive infinity, due to the fact that we are trying to divide by a number that approaches 0 at the center of the graph. Also, the colors depicting the angle of the complex function are now the mirror image of what they were before. This is because when we divide by a complex number, its angle is subtracted from the angle of the result. Now let us consider this function. This function has two places where the magnitude of the output approaches infinity, and one place where the magnitude of the output approaches 0. The one place where the output approaches 0 is the one place where the function's numerator approaches 0. The two places where the denominator approaches 0 are the only two places where the output approaches infinity. K is a constant. If we change the value of this constant, then we change the locations where the magnitude of the function approaches infinity. Let's call the places where the magnitude becomes infinity the poles of the function. And let us call the place where the magnitude becomes 0 the zero of the function. As k becomes very large, one of the poles moves far away, while the other pole approaches the location of the 0. When k is exactly equal to 4, the two poles are at the same location. The two poles are also at the same location when k is exactly equal to -4. And when k becomes a very large negative number, one of the poles again moves far away, while the other pole again approaches the location of the 0. Now let us consider this function. The exponential of a complex number looks like the following. If the imaginary part of the complex number is 0, then this formula becomes a simple exponential. And an exponential function plotted on a logarithmic scale looks like a straight line. On the other hand, if the real part of the complex number is 0, then we get this result, where the magnitude of the function is always exactly equal to 1, and it is only the phase of the output that changes. As it turns out, e raised to the power of a complex number has the following formula. A complex number with a magnitude of 1 can be written as follows. By rearranging the terms and using the properties of trigonometry, we can get the following formula for the cosine of an imaginary number. And we can get the following formula for the sine of an imaginary number. Although the sine and cosine of any real number always has a magnitude less than or equal to 1, the magnitude of the sine and cosine of an imaginary number grows exponentially. The plot for the sine of the inverse of an imaginary number looks like this.